When we left off the last video, we were talking about answering at least one questions, like if you roll 5 dice, what's the probability of at least one of them being a 3, by sort of coming at them from the back way, by finding 1 minus the probability that none of them is, that all of them are not. So here's another example of that. In a box of 30 chocolates, 4 have coconut in them. Oh no, we don't want one of those. But if you don't know which is which, and you just take 2 at random, what is the probability of getting at least one of the coconut ones? There's those words, at least one. So we're going to do that by taking 1 minus the probability of getting none of the coconut ones. That is, if you take 2 at random, what's the probability that instead of at least one of them being coconut, the first one is not coconut and the second one's not coconut? So the probability of the first one not being coconut would be the number of ways that could happen out of the number of outcomes in all. So if there are 4 that are coconut, the other 26 do not have coconut. So the probability of getting one of those that does not have coconut would be 26 out of 30. And then in that case, under that condition, the probability of the second one you pull out not being coconut, if the first one was not coconut, would be 25 out of 29. Because this time there's 29 left to choose from, and those include 25 that do not have coconut. So by taking 26 over 30 times 25 over 29, we get the probability that none of them have coconut. The first one does not, and the second one does not. And then 1 minus that gives us the probability that at least one does. And when we do the calculations, that turns out to be 0.253. 1 minus 26 over 30 times 25 over 29. And the parentheses aren't strictly necessary. It would still work out fine if I left them out, but I'm putting them in to make it a little more obvious what's going on. We take 26 over 30 times 25 over 29, and then that gets subtracted from 1. And if you're using a scientific calculator or graphing calculator that follows the rules for the order of operations, it will do this in the right order, and it will give you 0.25287 something. And if we round to 3 places, 0.2528 something rounds to 0.253 as the nearest thousandth. Next example. Suppose 60% of all people like broccoli. If you invite 3 friends over, what's the probability that at least one of them will like broccoli? Okay, at least one will is the complement that none of them will, that all 3 will not. The first one will not, and the second one will not, and the third one will not. So that would be 1 minus, okay, if the probability of liking broccoli is 60%, the probability of not liking broccoli would be 40%. So 1 minus 0.40 times 0.40 times 0.40, and that works out to be 1 minus 0.064, which is 0.936. Now, I'm going to end this section with a bonus example. It gets a little more complicated than some of the other examples, but it's a fairly famous probability problem. In a class with 30 children, how likely is it that 2 or more of them have the same birthday? You get a group of 30 people, like the 30 kids in a class. How likely do you think it is that you got 2 kids in the class who have the same birthday as each other? Now, assume that nobody was born on February 29th. I mean, if that were a possibility, that would make the calculations a little more complicated because that's leap year day and it only comes around once every 4 years, but it doesn't change things very much. So just to keep things simple, we'll ignore that. And we'll assume that there are no twins in the class, because if there were, then of course they would have the same birthday. So you just got 30 random kids. What do you think the probability is? Before I show you the answer, take a guess. It's one of these four answers. It's either around 8.2%, or it's around 33.3%, or 70.6%, or it's a 91.8% chance. So before I give you the answer, I'm going to try to explain how this is calculated. Either every child in the class has a different birthday, so there's all 30 kids with different birthdays from each other, 30 different days, or there are at least two who share a birthday. So those are the two alternatives. Those are the complementary events. And it's easier to calculate the probability that they all have different birthdays, that there aren't anybody in the class that has the same birthday as anybody else. So then if we can calculate the probability that they're all different, then 1 minus that probability would be the probability that somebody has the same birthday as somebody else, that they're not all different, that two kids at least share a birthday. Now suppose there were only two children in the class, say Alice and Billy. The probability that they have different birthdays would mean that Billy's birthday is on a different day from Alice's. And that probability would be 364 over 365. Because there's 364 days that Billy's birthday could be that would make it different from Alice's out of 365 days in all. Now what if there are three children, say Alice, Billy, and Chuck? The probability that all three birthdays are different, that means that Billy's is different from Alice's, and Chuck's is different from either of the other two. We already know that the probability that Billy's birthday is on a different day from Alice's would be 364 over 365. Then along comes Chuck, and there are 363 different days that his birthday could be that would make it different from either the other two out of 365 possibilities in all. So the probability that Billy's birthday is different from Alice's and Chuck's is different from either of the other two would be 364 over 365 times 363 over 365. If there were four children, say Alice, Billy, Chuck, and Darlene, the probability that all four birthdays are different would be probability that Billy's is different from Alice's times the probability that Chuck's is different from either Alice or Billy's times the probability that Darlene's birthday is on one of the 362 days that isn't already taken by Alice, Billy, or Chuck. And so on. Each time we have one more kid, we multiply on one more fraction in this pattern. So by the time we've got 30 children, the probability that all 30 birthdays are different would be a whole bunch of these fractions multiplied together, ending with 336 over 365. And then if you actually do the calculations, multiply that all out, it comes out to about 0.294. So remember, that's the probability that all 30 birthdays are different. There's a 29.4% chance that everybody in the class has a different birthday from everybody else. So that means the probability that they're not all different, that somebody shares a birthday with somebody else, is about 1 minus that, 1 minus 0.294, which would be 0.706. So the correct answer is 70.6%. In a class with 30 kids, there's a 70.6% chance that at least two of them have the same birthday as each other. In fact, this graph here shows the relationship between the number of people in a group and the probability that there's a pair who share the same birthday. So once you get to 23 people, that's when the probability becomes 50-50. If there are 23 people in the group, there's about a 50% chance of a pair of two people who have the same birthday as each other. Once you get more than 23 people, it's more likely than not. Once you get up to about 50 or 60 people, it becomes almost a sure thing. With a group of 60 people, it's almost for sure that somebody in that group shares a birthday with somebody else.